Hello class, welcome back to the dojo. It's me, the number ninja, or the sensei, or Jacob. And today we're actually going to be going into more detail on the laws of exponents that we learned last time. So last time we kind of just talked about what the laws were and did some very basic examples. Today we're going to be applying them in a more rigorous way. So we're going to be doing some harder examples, quite a few examples actually, just to help you guys get a better feel for how to actually use these rules, just because they are going to be so important moving forward. I'm going to encourage you guys to try as many of these as you can. I tried to make them all a little bit different so you'd be learning new things with each question. But I also think the easiest way to actually learn these is to try them yourself. You might not get them all, that's totally fine. I'm going to go over all of them. But when we're about to start a question, I'm just going to recommend that you guys, pause it, try the exact same question on your own, and then see if you can get the right answer. It should be a lot easier for you guys to pick it up than just watching me do it. Obviously, if you have any homework questions that are the same, you can try those as well, and it's the same idea. It's just really a matter of actually using the tools that we're kind of going over here. All right, so without further ado here, let's jump into some of our first examples. We're going to be beginning with the power of power law. So if you recall from last time, this was actually a rule that says if we have an exponent or a variable raised to an exponent, and that itself is then raised to another exponent, what we actually do is we multiply these values together and get our new value, which has an exponent of 6. And the reason for that we touched on last time, but I'll go over it one more time really quickly, is we're basically saying we have x squared, but this 3 power here means we have 3x squared all multiplying together. So we actually have x squared times x squared times x squared. And if we remember our other law, which was actually the product of powers law, that tells us that if we're multiplying values together with the same base, we can actually just combine their exponents with addition. So 2 plus 2 plus 2 is 6. This is usually more annoying and takes longer to write out, which is what the power of power law helps us avoid. Save some time there. Okay, so with that being said, let's actually start with our first example. This one is a little bit different because we actually have multiple values inside of our parentheses that are also all experiencing this power. So this is something you're going to see quite a bit. It's not that bad. All we really need to do is actually do something called distributing, which will come up a lot more in the future, but distributing this one exponent into all 3 of our different values inside of our parentheses. So that means what we actually end up getting is our 3 goes to the third power. Our x gets an extra third power added to it. So remember, using the power of powers law that we just talked about, that actually becomes a 6. And then we're going to do the same thing with our y. So the y goes from a 4 times 3, makes it y to the 12th power. And we can actually do or simplify the 3 to the third power. 3 times 3 is 9, and then we would do 9 times 3, which is 27. So our final answer would actually look like this. 27, x to the 6th power, y to the 12th power. Hopefully that one wasn't too bad. We're going to jump into the next one here. Again, pause as you see fit. I'll leave this on so you can see the example from before. Again, I recommend that you pause, try this one out. It's very similar to the previous one. See if you guys can get it. And we're going to jump into it now. So hopefully you already did it if you wanted to. Same idea. We're going to distribute our exponent to all 3 of our terms in here. And we're going to do the same thing as last time, basically. So 5 becomes 5 squared. X 3 times 2 is still 6, so it becomes a 6. And then the y, this is an important point. Numbers and variables have a default exponent of 1. So this y doesn't actually have an exponent here. That means there's a 1 in its place. We just don't write it because having a 1 doesn't actually change the value. Which means what we're actually doing for this is 1 times 2 for our y value, which gets us 2. And this is something you just kind of have to remember, but it comes up a lot. If there's no exponent written down, it is a 1. That's what it defaults to. Okay. Next, let's move on to one last example here. Just kidding, there's 2 examples. One more, there's 3 examples, wow. One more example. Again, pause it, try it. I'm gonna stop saying that now, so hopefully you guys get the gist. Same thing, we distribute to our 3 different values in here. We get 7 to the 4th power. Forgot to say, 5 squared is 25, right? 5 times 5. So the full answer that most people are gonna be looking for is actually this, with a 25 instead. All right, A is 12 times 4, which is actually on our times table, so hopefully you know it, but just in case. 4 times 2 is 8, 4 times 1, 4, so 48, which is a big value for sure. Luckily, we don't have to actually use this for anything because we just have a variable there. And then we're gonna do the same thing with B. 3 times 4 is 12. 7 times 4, that's a big number, so I'm just gonna get that number on a calculator. And it's actually, should show something different probably. It's 2,401. So if you actually did that yourself, good job, congratulations. That's a big number though. So, boom, 2,401, A to the 48, B to the 12. So this one, you know, I kind of put this in just to show you can get very large numbers, but the process is still the same. So hopefully you don't get too freaked out if you ever do see big numbers. We're just doing the same steps. Our numbers are just going to be a little bit bigger, but it doesn't actually change how we're solving it. All right, one more similar example here, and then we'll talk about this last one with this negative sign. Same idea. This one, there's a 3rd variable, but that doesn't actually change anything. We still just distribute to all of our values, this time 4 values, but it's still the same. So again, no matter how many values you have, we just want to move this exponent out to every single one of them. That's kind of the main idea. So this becomes 4 to the 5th. X is 10 and 5, which would be 50. Y is 3 to the 5th, so 3 5 times, which is 15. And Z, this is actually a callback to earlier. That's a 1, right? So we're actually doing 1 times 5, and we get 5. Same thing with the 4. This one's not as difficult, but we're not going to do the multiplying. We actually get 256 for that one. I think I did that right. So 256, X to the 50, Y to the 15, and Z to the 5th. All right, so now let's talk about this one last example here. I made this one for a specific reason, and then there's a little hint of what we're getting to next. But the key thing about this one that makes it different and what we're going to focus on is this negative sign here. This, unless the parentheses say otherwise, applies only to this 4. So what that actually means is everything else is going to be the same. So I'm just going to do that really quick. 2, 3 is 6. 2, 3 is 6 again. And 5, 3 is 15. But the key thing here is this 3 distributes to the negative 4 as a whole value here, as a partnered pair. So it's actually negative 4 to the 3rd power. And why this is important is because it allows me to tell you guys something that we haven't actually had the chance to cover yet. How do negative numbers work with exponents? It's a simple rule, you just have to remember it. If we have an even exponent, so that's going to be something like 2, 4, 6. You guys know what even numbers are, I hope. No matter what the value is, here, let me put even exponent. No matter what the value is, we will get a positive answer. Okay? The reason for that goes back to the idea of what the exponent actually means, right? If we have even a negative number to an even power, what that means is we're multiplying negative 2 times negative 2. And if you remember, 2 negatives multiplied together is a positive value. So this ends up being a positive 4. And because they pair up like this, as long as we have an even exponent, there'll always be a perfect number of pairs to get a positive value. The number will be bigger the more you have, but it'll always be positive. Now, for our negative exponents, I'm kind of running out of space, so I'm just going to do this. For our negative, I just said that wrong. For our odd exponents, if we have an odd exponent, the rule is different. This is going to be, 1, 3, 5, etc. We don't end up with positive necessarily, we just end up with the same sign we already have. That is because the pairing doesn't actually happen when we have an odd exponent. All right, let's do the -2 again. If we have to the third power, that means we're doing -2 times -2 times -2. So there's actually an extra negative after we pair these up into a positive, and then we end up with a +4 times a -2. Which, remember, a positive times a negative is a negative. So we actually get -8. And that's the main idea. As long as it's an odd exponent, there will always be one extra that's an odd man out. So it will remain the sign you have. If we have positive numbers, if these were all positive, then we'd just be multiplying positive numbers the whole time. And a positive times a positive is a positive. So it doesn't matter that there's an extra one because the sign has never changed to negative in the first place. Hopefully that makes sense. What that means is in this example, we actually do end up with a negative number because there are 3 of them and it started negative. And 4 to the third power is 64, so we get a -64. And then the other values stay the same. So yeah, hopefully that was a good example there for you guys on that one. Next, we're going to jump into our next batch of examples here, which is going to be our product of powers and our quotient of powers. And again, I kept these together because they're very similar. They're just adding versus subtracting. So as a recap, product of powers is if we have 2 bases that are the same and they're multiplying together, we can add their exponents. Quotient of product is the opposite. If we're dividing 2 bases that are the same, we can subtract their exponents. So 2 plus 4 is 6, 5 minus 2 is 3. Hopefully we remember that. If not, there you go. But we can actually make these a little bit more complex. So as we go through here, they're going to be getting harder and harder. But again, try them if you can. Let's begin with this first example on our product of powers. What we do is, this is first of all called a coefficient. That is a value, a number usually, that is in front of a variable. Forget usually, always. A number that is in front of a variable. This is called the coefficient. Whenever we're doing questions that have variables and coefficients, we actually do all of them separately. So we do all the coefficients together as part of the problem, and we do all the variables as part of the problem, but they don't really interact with each other. And just to show you what that would look like, we're actually just going to do multiplying of 4 and 3 first, because that's how we would solve this, to get the value 12. And then we're going to do separately our variables doing our product of powers rule to get a squared times a to the 4th, which would still be a to the 6th. So that's kind of how that works, is we're always just going to do the coefficients and then the variables and then kind of put our answers together at the end. So same idea happens with the quotient of product law. Now it's a fraction bar, right? So we're dividing this 10 into 2. And we're going to do that first to get our 5, and then we're going to subtract our exponents and get x to the 3rd. Hopefully those weren't too bad. One extra level of difficulty that you can see with power or with multiplying here is that we can actually have fractions instead, but it's going to be the same thing. I kind of just included this to talk about fractions. So the x's are going to multiply exactly the same. We're going to get x to the 10th in this case because we're just adding them together. Now the fractions, again, we're going to do it the same way, but we're going to multiply it the way fractions are multiplied, which, if you don't remember, is just across the top and across the bottom separately. So we're going to end up with a fraction still, but in our numerator, which is the top of a fraction, we're going to get 1 times 7, which is just 7. And in our denominator, which is the bottom of a fraction, we're going to get 4 times 2, which is 8. So that's just a quick refresher of how multiplying fractions work, in case you forgot. Just across the top is one part, across the bottom is the other. All right, so now let's talk about negative exponents and how that applies to both of these rules. That, if you remember, was a different law, but now we're actually going to be talking about it in conjunction with these 2 rules right here. It doesn't change too much, but it's a little bit counterintuitive at first, so I just wanted to talk about it. we're going to keep the same idea, right? We have the same basis here. Y is the same as y, which means we add together our exponents. But our second exponent is negative. It's a -2, which is why this comes back to actually, I believe, our second video in the series here, where we talked about how to combine these if they have different signs. And what we discovered there is if they have different signs, we subtract them. So even though the rule says we're adding, that is what we're doing. It's just in this specific case, we go through our list of what we're supposed to do when we add, right? So we're supposed to add them, which means we check to see the signs. Here they are different signs, so we will subtract the values, which means we're still going to have our y, but we're actually going to do 4 minus 2, which is just a +2, and we keep the sign, remember, of our number further away from 0, which is the 4. As you can see, all of the things we've talked about before are now kind of combining together into one super problem. And the problems are just going to keep getting more and more super, so it's kind of important that we understand every step of the process, that way we can add them together. The same thing would happen on our quotient one over here. Again, quotient one is subtracting. So what we're actually doing is subtracting our two exponents. We're doing 3 minus our -2. And here's where, again, something we talked about in the second video comes into play. 2 minus signs means we're actually adding these together. So it's actually going to be 3 plus the 2. And we actually end up with a to the 5th power in our numerator, which is just where it normally goes if we're doing quotient rule. Whatever value we get is the value of our numerator. That's important because sometimes we will get a negative value in the numerator, and then we were going to have to actually move it down to the denominator, which is coming up in our next example. So now let's do one more example of each here before getting into our last topic of the day. Again, now you see we have the fractions, we have our product or power of products, and we have our negative exponents all coming to a head at once here. So again, we're going to start by doing our fractions separately. So 1 times 4 is 4, 2 times 9 is 18. This is actually a simplifiable fraction, so we're going to talk about that at the end as well. Next, we're going to try to do our variables. So it's multiplying, which means we're adding them together. So we're doing this 2 plus this -6, which means we actually get different signs, so we're going to subtract them. We end up with a -4 there. So this is actually our answer, but it's not at all in the simplified form, so we're going to talk about how to do that. One thing to keep in mind is if we ever see a variable off to the side of a fraction like this, that means it's actually in the numerator. It's just to make it easier to understand, a lot of times we write it separately. But if it's ever off to the side, it is in the numerator. So our fraction here can simplify, which, remember, just means if we have factors in common from the top and the bottom, or the numerator and the denominator, we can divide them out to get a smaller fraction. Or not a smaller fraction, because it's actually the same value, but a fraction with smaller numbers that is easier for us to understand and do more work with. So we always simplify when possible. Here, these are both even, and just a little trick to remember is whenever numbers are even, you can always divide both of them by 2. So we're actually going to divide the top and the bottom by 2, and 4 divided by 2. So I should have written this on the other side, because that's actually what's happening, but it did not fit. So we're actually doing 4 divided by 2, which is 2, and we are doing 18 divided by 2, which is 9. So that's now our simplified fraction. And then the other thing that we have to realize is our negative exponent, if you remember what that meant from our negative exponent law, actually means it should be in the opposite side of the fraction. Let's actually expand this out. Our a to the -4 is going to travel down to the denominator to get rid of that negative value. And it's just going to become a to the 4th power. So that one was probably our most complicated one yet, just because we had so many things going on. But that's how we would solve that, and hopefully that was helpful. Now we're going to do a similar thing on the right-hand side here with our quotient. Again, we have negative exponents. Again, we're going to worry about those later and start with our coefficients. 16 divided by 4 is just 4. So here we we had a nice even number, but sometimes you will have to just do simplifying like we did on the left. Next, we're going to do our exponents. So it's -2, and we're doing division, so it's subtraction. So we're going to do -7 here, which is -9. And if you remember what I said earlier, that's the value for our numerator. So it's actually y to the -9 on top. And then because we're 4 divided out and we subtracted, there's technically currently only a 1 in the denominator. Similar to what we were talking about before, where the default exponent is 1, the default denominator is also 1. So you don't actually have to write this out. It's implied if there's no denominator that the denominator is 1. However, because we have a negative exponent, we actually have to move our y into the denominator for this question. So we're going to keep our 4 on top, but then our y moves to the bottom and becomes a 9. Cool. So that's everything we had there. And then one last thing to talk about, this one's the easiest, so it's going to be pretty quick, is the zero exponent law. If you remember from before, all that is that any value, doesn't matter what it is, to the zero exponent is always a 1. But we're going to talk about really quickly what that means if we have it in conjunction with other variables or other values or other powers, that kind of thing. All it means is the number that it is actually an exponent for becomes a 1. So in this case, the x is the only thing that becomes a 1. And we get 1 y to the third power, which almost every time will just be written as y to the third power, because the 1, again, is implied. You don't have to write it. So this one, not that difficult. We're going to talk about this now. This is product of powers. If you see, we have the same base, so we're good. Same idea. We're going to do our our coefficients first. So 3 times 5 is 15. And then we're going to handle our values here. So this one, it's a mistake people make a lot with the exponents, is they multiply the 2 and the 0 together and get 0 canceling out the x. But remember, we are doing product of powers, sorry. So it's actually adding our exponents together. So it's 2 plus 0, which is still just 2. So as you can see, all that actually happened is this became a 1, which is why nothing else changed except for this. So now let's talk about power of powers and how the 0 works here. Same idea. The only thing that's actually going to be affected is this term right here. So normally, or everything else goes as normal. We're going to distribute this out to everything, but it becomes 6 to the third. A is a 1, so it becomes a to the third. B is a 3, so it becomes b to the 9. And then here, remember, this is where we're actually multiplying our exponent with our other exponent. So we actually get c to the 0, which, if you remember, just becomes a 1. And then 1 doesn't change our values, so we don't even have to write that. So this would be our answer. 6 to the third power is 216, I believe. So yeah, 6 to the third power is 216. So we actually end up with 216 a to the third power, b to the 9th power. Let me actually center these since we're not really doing the rest of the page. Okay. Now, but what happens if our power or exponent to the rest of the exponents is 0? Well, now the whole term, as you see, because it's outside the parentheses, our whole exponent or our whole parenthesis become to the 0 power. So right, because 6 to the 0, 1 times 0 is 0. A is the same thing, 1 times 0 is 0. B is 3 times 0, which is 0. And C is 2 times 0, which is 0. And they're all 0 powers, which means they're all 1s, which means it's just 1 as our final answer. The same thing ends up applying in our quotients if we have any fractions. Only the value directly affected changes. So in this one, x to the 0, something to the 0 power is 1, but our y is still to the third, so we end up with the final answer of 1 over y to the third power. So sorry if I was speaking a little fast. I knew this one was going to be a little long and I didn't want the video to be too long. We covered quite a few things, really got to use the rules we talked about last time, so hopefully getting some more difficult examples was helpful for you guys. Hopefully you were able to solve some of them on your own. If you weren't, no problem. Trying them also helps kind of fire your brain neurons and get learning on how to actually do it. If you do have any practice problems that your teacher gave you, or maybe any homework ones that you didn't do, definitely recommend going back and trying those again now that you have more of an understanding of how the rules work. And again, you saw today the first time where something we talked about before came up again, and we actually combined multiple different things that we had talked about before. And that's going to keep happening. Especially in pre-algebra, everything we talk about now, we're only talking about it to use it in harder questions later. So very important that you know what we're talking about, but hopefully you guys were able to learn a lot today. And yeah, I'll see you guys for our next session. Good training and goodbye.